technology. He is delivering on the topic canonical forms. Now over to Professor Mandeep Singh.
Thank you, Professor Rajesh. So let us start with the canonical forms. So we shall be giving a quick look on the definitions and basic results. So let V be a finite dimensional vector space over field F. Okay, field F for K, whatever you want. And T, say, suppose is an operator belonging to this set. This is a set of all linear operators on V. And if V is a vector space of finite dimension n, then the dimension of, let us say, dimension V over F is n. Then dimension LV over F would be n square. Rather, this is not only vector space. This is an algebra. In fact, the composition of the operators is also included in that. So we say lambda belonging to F is an eigenvalue of T if there exists a non-zero vector X or V, whatever you just choose. Let me choose V in V, such that P of V is exactly lambda times V. Okay. This is same as to say that kernel of T minus lambda I is non-zero, because this is same as to say T minus lambda I of V is 0, right? And kernel T minus lambda I is also known as the eigenspace with respect to eigenvalue lambda. All right. So let us now have a look on some equivalent forms of the result. Lambda is an eigenvalue. Lambda is an eigenvalue of T. Then second is kernel T minus lambda I is not equal to 0. Third part is rank T minus lambda I is less than the dimension V over F, which I just took as n. Fourth is determinant T minus lambda I is 0. These are equivalent forms of this. See, this we have seen here. Rank means the range space of T minus lambda I. Using rank nullity theorem here, you can prove these 3 and 4 easily. Okay, then we come to the minimal polynomial. See, LV, we just noted that this is an algebra over F with dimension n square. Then what is the quick look on this? I which is I just take t raised to the power 0, then t square, and so on, t raised to the power n square. Means these are the compositions of t. This is 2 times composition of t. This is n square times the composition of t. These are the elements here in LV. Okay. The dimension of LV is n square. These are n square plus 1 elements. So obviously, if the dimension of this is n square, then any n square plus 1 elements of that vector space would be linearly dependent. These would be linearly dependent. Okay. So we may have some alpha naught, alpha 1, and so on, alpha n square, such that these are in F. Okay. Such that alpha naught into I plus alpha 1 into t plus alpha 2 into t square, and so on, alpha n square t n square. This is equal to 0. These are not all alpha i's equal to 0. This is what linearly dependent means. Okay. This immediately provides me an information that T satisfies a polynomial that is, say, fx given by alpha naught plus alpha 1x plus and so on alpha n square x n square. Right? If T satisfies this polynomial, then obviously I may now assume a polynomial which is satisfied by T having least degree and monic. Monic means the leading coefficient of this polynomial, which is this, should be 1. So a monic polynomial of least degree, which is
Sir, there is alpha is not equal to 0. You have written, so this is alpha is equal to 0.
where what
Not all alpha is equal to 0, but you have written.
only then this would be linearly dependent. These would be linearly dependent. If all alpha is would be 0, then they
not
would
all alpha I equal to 0, right?
You have written not equal to, so
They put not equal to.
Oh, sorry. Yeah. Let me just make that correct. Okay. Not all alpha is 0. Okay. Which is satisfied by T. Right? Monic polynomial of least degree, which is satisfied by T, is known as minimal polynomial of T. Okay. Now, this part takes no guarantee for the degree of minimal polynomial. So far, we have degree of minimal polynomial, which is less than or equal to n square. All right. We shall be working on that. But before that, I must be just stating a theorem, which is known as primary decomposition theorem. We are now straight away going to this theorem. Okay. And then we shall be working on the degree of this minimal polynomial. But that states, let V over F be a finite dimensional vector space, right? And let T belongs to LV, right? with minimal polynomial. We shall be denoting this minimal polynomial here by mtx. Okay. So throughout we shall be taking mtx as minimal polynomial of t with, okay, with mtx as p1 x raised to the power r1, p2 x raised to the power r2, and so on, pkx raised to the power rk, where pi is x are irreducible polynomials. Irreducible polynomial means they are not further reducible, means they cannot be factored further. Okay. Ri's r1, r2 are positive integers. Are positive integers. Okay. Then V can be decomposed as V1, direct sum V2, direct sum, and so on, Vk, where these VIs are the kernels of Pi t raised to the power r. Okay. Right. Further, in addition to this, if TIs, these VIs, basically they are T invariant subspaces. T invariant subspaces are what? For which T of Vi is contained in Vi. Okay. In addition, if Ti is an induced operator, just example, induced operator of T on each Vi, then MTI x is exactly Pix raised to the power Ri. All right. So here let me just introduce with you by this induced operator Ti. Ti means if W is a T invariant subspace of V, then Ti is an operator on W such that Ti of W is exactly T of W. Right? This is called induced operator. This is also an operator. Okay, but this is on W. So let us just go by the proof of this. Proof is which is sketched like that. We shall now define for each I as a polynomial Qi x, which is given by mtx divided by Pix raised to the power r. Means if you just take out this factor Pix from this mtx, then it is known as Qix. Obviously, you may see this Q1x, Q2x, and these Qkx. These are the k polynomials. The GCD of these polynomials would come out to be 1. Okay. And if GCD of these is 1, then by simple algebra, there exists AI axis in Fx such that A1x into Q1x plus A2x into Q2x plus and so on AKX into QKX this is equal to 1. This is equal to 1. All right. And that immediately provides me, this is A1t, Q1t plus A2t, Q2t, and so on, AKT, QKT as identity operator, right? If this is an identity operator, then any vector which is taken in V, when we apply identity to that, that would give me this as V. So I get here A1t, Q1t, V plus A2t, Q2t, V, and so on, AKT, QKT applied on V. All right. So I just decomposed any vector in V as the sum of these vectors. Let us see what are these vectors. If I just rename them as V1 plus V2 and so on, Vk, let us check what are these VIs. Vi, which is same as AIT, QIT applied on V. Exactly, right? Right? If I just apply PIT raised to the power RI on this VI, you check that this is AIT and PIT into QIT, this would complete your MT of T applied on V. Since this is the minimal polynomial of T, so this is 0, and 0 operator takes every vector to 0. So this is a 0 vector. All right. So that means what? Now this is a guarantee that Vi belongs to kernel of PIT raised to the power R. Okay. So this immediately provides me this decomposition of V as the sum of V1, V2, and Vk. So far we are to prove the sum as direct. So for direct, we are to prove that every vector is uniquely written as the sum of the vectors from these VIs. Okay. So for that, what we need? We need that if V1 plus V2 plus Vk is equal to 0, where Vi is belonging to these VIs, then each of Vi is none other than 0. Then only the theorem would be completed up to the direct sum, which I just claim up to here. All right. These are obviously kernel spaces and so invariant, key invariant. All right. So here, if this is 0, then I can write any of the Vi as the sum of other Vj's, but not Vi here. This is Vi plus 1 and the Vk. All right. All right. Now see this QIT of Vi. If I apply QIT on here, on this, that means Vi, the right side of Vi is the sum of these VIs. If I apply this here and look at that, then QIT, this contains PIs, P1, P2, PI minus 1, PI plus 1, but not PI, okay, as such, the factor. So V1 is in the kernel of P1T, which is present here. V2 is in the kernel of P2, t which is present here. So this would be 0. If I just apply qit on this vector, this would lead to 0. That means qit of vi is 0. Also, we have pi t ri. When I apply this on this side, this is 0. Okay. But since qit, qix and pix raised to the power ri, GCD of these is 1, then what happens? Again, I have b1x and b2x such that this is belonging to fx, such that pirix into b1x plus b2x into qix is equal to 1. But then qi. But then what happens if you apply this on vi? This is vi because this is identity operator. So identity takes vi to vi. Here, this part is already known to us 0. This part is already known to us as 0. So this means vi is 0. This is true for all i's. This is true for all i's. That means this sum is direct. That means this confirms that my v is decomposed as v1 direct sum v2 direct sum vk. Okay. Then what is left? We are left with the additional part, right? Additional part says that if ti is an induced operator of t on vi, then mti x is exactly pix raised to the power ri, right? See, while defining my minimal polynomial, this is the least degree polynomial. You see, if any other polynomial, this is the least degree polynomial, mtx is the least degree polynomial, which is satisfying t. Okay. If any other polynomial fx, which is satisfied by t, that means 0, then this divides this ft. This is a trivial result. You can just use divisional algorithm, and then using minimality of mtx, you would find that this must divide fx. So that fact would be used here, right? So notice that pi t raised to the power ri applied on vi is 0 or 0 for all vi's. Let me not write vi because vi means this is countable. This may not be. So let me write this v belonging to vi. All right, for all vi's. For, let me write here, for all. Hello. V. Hello. Hello. So this would be 0. Thus, if m, if mtix is the minimal polynomial, polynomial, then MTIX must be dividing PIX raised to the power RI. This means MTIX would be of the kind PIX raised to the power some SI, where SI is less than or equal to RI. We have to show that this is exactly equal to R. So if this is so, then look at this a polynomial fx, which is 2ix into pix raised to the power si. Hello. 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 Some participants have made their audio on. Please make that off. So fx is this. If fx is this, then obviously ft is 0, because ft takes every vector 0 in V. So if ft is 0, then obviously mt, this I just got this, ft is 0, mtx, this must divide fx, but fx is what? This, where qix would go with qix, but this would go only when ri is exactly equal to s. All right. So we got that, finally got that mtix is exactly pix raised to the power r. This is a fundamental important theorem for now canonical forms. Okay. Now we are going to the second part of this, which is hello. Yeah.
So can you please move a bit upwards?
Yeah.
Where you have defined the minimal polynomial of pi. Yeah, that just here. So you have taken that mtix divides pi to the power ri.
Yeah.
So how have you taken exactly to be pi to the power si? There can be some other multiple other than the pi.
This is the irreducible polynomial. Pix is irreducible polynomial. Mtx would divide this. That means this is pix raised to the power some si, which is s, where si is less than or equal to r.
Yeah, that I understand that it's an irreducible polynomial, but what I'm trying to say is that it can be some g times pi to the power ri. Cannot that happen?
But this is the induced operator. Ti is
Oh,
the,
got it. No, I got it. Thank you. Yeah.
okay. So let me now come to the part annihilator of the vectors. V belong to V. Okay. What is that? See, V is a vector space over F with dimension equal to n. Then you see T, if T is an operator, then V, comma T, V, comma T square V, and so on, T raised to the power NV. All these are all the elements of this V. And these are n plus 1 elements. What that indicates? That these are linearly dependent because the dimension of this is n. If the n plus 1 elements you are choosing from vector space V, then they are linearly dependent, which implies there exists beta naught, beta 1, and so on, beta n in F, not again, not all zeros, such that beta naught plus beta 1, this is V, beta 1 TV, and so on, beta n TNV, this is equal to 0. Is it all right? This is same as to say beta naught plus beta 1 T and so on plus beta n Tn applied on V is 0. This means I got a polynomial fx, or say f1x. I have taken fx above, which is beta naught plus beta 1x plus and so on beta n x raised to the power n, such that f1t when applied on this V is 0. That means every element satisfying somehow a polynomial like that. Again, if this is the guarantee, then I may choose the minimal polynomial. Which is denoted by, say, MT. Now T is taking into account because we are taking T here, and V is also taken into account, such that this is, hello,
Yes, sir. Yeah.
such that this is satisfied by that. Okay, satisfy which minimal polynomial such that MT of V of T applied on V is 0. Minimal polynomial means it is monic as well as of least degree. Again, since this is 0, also we have MT of T which is 0. That means if I apply V here, then that is also 0. This implies MT annihilator. This is known as annihilator. This means this divides MT of X. Okay. This polynomial is known as annihilator. MTVX is known as annihilator of V. Hello?
Yes, sir.
Some problem, electricity problem is there. Maybe I may lose internet connection for some time. But anyway, it is working now. Let us continue. Okay.
Okay, sir.
So this is the minimal polynomial, right? Which is known as annihilator. But
Hello, sir.
Hello. Yeah. Hello.
Yeah, sir. Actually, here you have defined minimal polynomial as MTV of T.
Yeah. This is with respect to the element. This is
Okay.
why this is known as annihilator of V. But
MT of X is general minimal.
General. That is a minimal polynomial of T. All right. Annihilator. But here, what is the degree? What can be the maximum degree of this? Can you guess it? Here the degree was not more than n. The degree of MTVX is less than n for all V's in V. Okay. Hello.
Yes, sir.
Yes. You carry on this. Otherwise, I may think that the connection is somewhere lost. So please speak out when I ask something. Okay.
Sir,
Yes.
here we are saying that MTB of X is annihilator of B, right?
Yeah.
So this is annihilator of B with respect to B, right? Because
yes.
if we change T,
Yeah, then it would
then,
be changed.
so this is annihilator of B with respect to B.
Yes, this is why T has been taken into account. All right.
Thank you, sir. Yes, sir.
Yeah. Degree of this, but this is sure that degree of every element, the degree of the annihilator of every element would be less than or equal to n, irrespective of transformation what we choose. All right.
Yes, sir.
Let me now control the degree of my minimal polynomials. So there is a proposition. This is let E over F be a finite dimensional vector space. And T belonging to LV, right? Then there exists a Y in V such that MTYX is exactly equal to MTX. See, this theorem is now would control the degree of my minimal polynomial. This is what my aim was. Okay. Hello.
Yes, sir.
Yes, sir.
Let me now go by the proof of this. So, because MTX we are considering as P1x raised to the power R1 plus P2x raised to the power R2. Sorry, not plus. This is the product into and so on. Pkx raised to the power Rk, right? Where these Pi's are distinct irreducible polynomials. Irreducible polynomials in Fx. All right. All right. So by using primary decomposition theorem, I just decompose my V into VI's. Now I can make use of the primary decomposition theorem to VK's, where VI's are the kernels of Pi T raised to the power R. Okay. Right. Okay. And Ti, if Ti is the induced, if Ti is the induced operator of T on Vi, then MTIX is exactly Pi x raised to the power R. This is what we have already proved. Now, I just look at Vi. Vi. Let us take some Yi which is belonging to Vi. Then my claim is, I claim that MT annihilator of this Yi is exactly Pix raised to the power Ri. If this is not so, if this is not exactly this, then certainly this would be of some, if there does not exist any yi such that mt of yix is exactly pix raised to the power ri, then what would happen? What would happen? Some polynomial is would be killing every element of vi. That means that is pit raised to the power ri minus 1 is 0 for all v's belonging to vi. But if this is so, then pi x raised to the power ri minus 1 would be the minimal polynomial. This would contradict the minimality of mtix. So there must be
Sir,
existing.
could you please explain the last portion again?
Yeah. Let me explain. See, I just say that there exists at least one yi in vi for which this would be exactly pix raised to the power ri. This is the annihilator of yi. Is it so? This is, I just say there exists at least one yi such that the annihilator of yi is exactly pix raised to the power ri. If not, then a polynomial of degree less than this would be killing each vi, which is like that, for all v's in vi's. Is it okay? Hello?
Hello, why exactly Ri minus 1? Could it be something like Ri minus k or something?
What can be the 1 degree less than that? You just think upon that. If you just make degree less of this polynomial, it is only possibility this, because pix is irreducible. It must be pix raised to the power something.
Okay, sir.
Okay. So this would contradict the minimality of mtix, and hence there exists at least one yi for which the annihilator of that yi would be exactly pix raised to the power ri. All right. And if
Yes,
so, then I can choose my y as y1 plus y2 plus and so on yk. These yj's are chosen in vj's such that mt of yj is exactly pj x raised to the power rj. Okay. Rj. Is it all right? Then I just look at mt of y of x. Right? I just look at this annihilator of this y. Can you think of what can this be? Because this divides mtx, so it must be of the kind p1x raised to the power some s1, p2x raised to the power some s2, and so on, pkx raised to the power some sk, where si's are less than or equal to ri's. Okay. I claim that these si's are none other than exactly ri's. Suppose there exists an index L such that SL is less than RL, then what happens? What happens? Then if I take, I defined earlier QL x, which was MTX divided by PLX raised to the power R. All right. QLX, I just defined that. Okay. If I just take this QLX and this PLX raised to the power SL, right? I take this polynomial, right? This is a polynomial to which my MTYX would be divided, right? MTYX would be divided. Now look at this QLX, PLX raised to the power SL. The beauty of this polynomial, what that says, QLT, PLT, SL, when applied on Y, what about that? This would kill this Y. Is it so? Is it so? That is, hello? Hello?
Yes,
Are you
yes,
there? So one person may be speaking, otherwise I feel that connection is lost. So this is 0. That means what happens? I1 to K. Yeah, then you just take the factors here. QLT, PLT, SL, and here YIs. This is 0. This means that. All right.
Yes, sir.
Is it so? Yeah. So what that indicates? Because QLT contains PIs except QPL. Except PL. So this would kill Y1, Y2, except YL, and all YKs. Okay. So from here, what happens? This PL would be particularly killing YL. So this means what I get is QLT, PLT raising power SL, YL is 0. Rest assured is they are killed by this QL. All right. Also, we have PLT SL, which is applied on YL. This is belonging to what? See here. This would lead to PLTYL belongs to sorry,
Kernel of
kernel. That is what I. This belongs to kernel QLT. All right. Can you just tell me about this? Yeah. QL. This is also belonging to kernel of PLT raised to the power RL. Is it so or not? Hello? Hello?
Yes, sir.
Yes,
Ah.
sir. Yes,
Yes,
sir.
sir. Yes, sir.
Yeah. You must be aware that this is a non-zero vector. Why? You check that this is an exercise.
Yeah, because the minimum we have
Because
related to be the power.
these yi's are chosen as per their annihilator is exactly pjx raised to the power rj. They would be only killed by them, not less power. So SL is something taken to be less, right? If this is so, then this belongs to the kernel of both, but this QLX and PLX raised to the power RLX, GCD of this is 1. If the GCD of this is 1, then this basically would lead to 0, which would be, this would be leading to 0, okay? This fact would lead to that PLT raised to the power SLYL0, which is contradicting the fact. It's non-zero part, okay? So what happens? I got this Y, I got finally this as Y, which is exactly that element whose annihilator is MTX, whose annihilator is MTX. And so this
Sir, can you repeat the last step?
Yeah. I just see, this is non-zero vector. And non-zero vector cannot belong to two kernels here. This is kernel QLT. This is kernel PLT raised to the power RL. GCD of these is 1. And then just look at this here. You just see this would lead to QLX into say alpha 1x plus PLX raised to the power RL, say alpha 2x is 1, and that leads to QLT alpha 1t plus P1t t raised to the power RL alpha 2t is equal to I. And when you apply YL to this is YL, and this side would be 0. So YL is 0, that means this is 0, which would contradict the fact. Okay.
And sir, when you said it is non-zero, it is because the annihilating
Because the
polynomial for YL was PL.
choice of YL can be only that element for which the annihilator of YL is exactly
PL for RL.
Therefore, this is not zero. Okay.
Sure.
So this has to be non-zero. So this proves that MTYX is exactly MTX, and that gives me the degree. So degree of MTX, this is the corollary. Degree of this is MTX is now less than or equal to n, because the degree of each annihilator we have stated is less than or equal to n. All right. Somewhere I have written about the notes. You just check. Yeah, this is the fact now used. So this controls the degree of the minimal polynomial. Now the question is how to find out this minimal polynomial. Okay, that we shall be doing in the tutorial class as well, right? We shall be doing that in tutorial class, how to find out the minimal polynomial. Hello?
Okay, sir.
Yeah. But let me tell you here, if V is a outline, V is a vector space with the dimension is equal to n, and suppose V1, V2, Vn is a basis. All right. And we know that if T belongs to LV, then MTX, which is the minimal polynomial of T, this, and we also get the annihilators of these VIs. See, the annihilators of these VIs would be dividing MTX. This I have told you. Can anybody just tell me the details of this? Hello? Hello?
Yes.
Can you tell me the details of this? I just told something before this proposition that each annihilator would be dividing MTX. Are you convinced with this? Hello? Hello? Check. I have some variation.
Yes, sir.
This divides. So that means what? If this is dividing this, this means LCM of these empty VI's X, that also divides MTX. It divides, okay? If these divide that, then LCM is also dividing that.
Yes, sir.
Then can you just guess what I want to say? LCM
So
of
that MC
LCM of this for all i's, if that is a fx, that means fx divides MTX. Okay. Can you just tell
Will
me?
it be equal to MTX?
Equality?
This must be equal because
Yeah, because this LCM
LCM would
divides
be divided.
NLM.
This LCM, if this is fx, then f of t of v is 0 for all v's in v, and hence ft is 0. And if ft is 0, then MTX would divide fx. On one side it is dividing MTX, on other side it is dividing fx. So MTX is same as fx. All right.
Yes, sir.
So what we do in a numerical examples, what we do, if we are given with an operator means some matrix with respect to a basis. If you are given with a matrix, then you just find out the basis of the vector space over which that matrix is defined. And if you just get the annihilators of that basis, take their LCM, that would be the minimal polynomial of this. This is what we are going to do in the tutorial sections. Okay. Then we come to the, now we are coming to the
Sir,
hello.
Your last proposition,
Yeah.
it also implies that the minimal polynomial of a operator T
Yeah.
would be of a degree less than equal to n, right?
This is what I did. Yes.
Yeah, okay. You already have said it.
This is why we have done this proposition.
Yeah. And sir, we also know Cayley-Hamilton.
Cayley-Hamilton theorem says that now Cayley-Hamilton theorem is useful. Every minimal polynomial divides characteristic polynomial.
Characteristic polynomial.
Yeah, got my point. Minimal polynomial of T divides the characteristic polynomial of T. This is the Cayley-Hamilton theorem. Hello.
Yes, sir.
Yes,
Right,
sir.
sir.
Got my point?
Yes, sir.
Yes, sir.
Yeah. So see here, now we are going to diagonalization of the diagonalization means if T is any operator in LV, then there exists a basis B, a basis of B such that matrix of T with respect to this basis is diagonalized.
जल्दी जल्दी रह क्यों मैंने चार्जर डाला और
Hello.
धन्यवाद
Right? So we are going to now find out a basis under which this T is diagonalized. So first proposition here, eigenvectors,
आपने बोला ध्यान दूंगा दे दिया आज
vectors corresponding to distinct eigenvalues of a linear operator T in LV are linearly independent. Okay. Proof is easy. Just look at that. Since T belongs to LV, and if x1, x2, xn be the eigenvectors of T x not, let me not take xn, because if the dimension is n, then these are the all eigenvectors. I just take q, eigenvectors of T with respect to eigenvalues lambda 1, lambda 2, lambda 3. Okay, they are distinct, right? Then I define an operator Sj, which is given by composition. Here product means composition. I1 to k, but I is not equal to j, such that lambda j minus lambda I, inverse of that, here I just take T minus lambda I into identity. This is an operator. I just take the composition. This product means composition. All right. This belongs to LV, because LV, I just in the beginning told you that this is an algebra. If this is an algebra, then this is belonging to LV. Okay. Now you just check Sj when applied on xk or xt. XL, what are you getting from here? Can you just look at this and calculations, immediate calculations, quick calculations. Yeah. This is exactly XL if J is equal to L and 0 otherwise. Okay. 0 otherwise. Is it okay? Hello? Hello? Yes.
Yes, sir.
Is it okay?
Yes, sir. Yes, sir.
Yeah. If this is so, then I just assume, now take summation alpha I xi I ranging from 1 to k is equal to 0. I am to prove that these are linearly independent. For linearly independent, I must be taking this linear combination equal to 0 and proving that each alpha is 0. Each alpha is 0. Okay. Now you see 0 is equal to yes. Hello.
Hello, sir, I did not understand the previous.
This step.
SJXL equal to 0.
Yeah. This one.
Yes.
See, when we are, what is our aim? Our aim is to prove that eigenvectors corresponding to distinct eigenvalues of a linear operator T belonging to LV are linearly independent. Then aim is to be achieved only if you consider this combination as 0 implies each alpha is
the previous thing. Previous one.
Which one? This one? Now you see these are distinct eigenvalues. Distinct eigenvalues, then I define Sj as product I1 to k lambda j minus lambda I inverse of that, because they are distinct. So this cannot be 0. And so I can take the inverse of that, but I is not equal to j here. I just take out j. J, this product is over I only. Okay. Hello.
Yes, sir.
This is T minus lambda I into I. And this is an operator which is in LV, because LV is an algebra. This is the composition of the operators. All right. And now if you look at this operator which is applied on XL, where XL is one of the elements of this X1, X2, Xk. See what is the action of Xj on XL. Check that. Easy to check. When you apply XL here, XL, because this is an eigenvector, so this would give lambda L XL. This is lambda I XL. So XL would be out. So here what is left? Lambda L minus lambda I. Now I just don't put any restriction on L. L is any of 1 to k. As I would be equal to L, that would make this 0, Sj 0. Right?
Sir, wouldn't it be XL if J not equal to L?
This is otherwise, this is why I write. If this is J is equal to L, then this is exactly L. XL or Xj. All right?
Yes.
This is 0 otherwise. So here, if you apply this on this vector I1 to k, alpha I, xi, this would lead to alpha L into xl. But since these are eigenvectors, therefore they are non-zero, this implies alpha L has to be 0 for all else. And that means this set is linearly independent. This set is linearly independent. Okay. That is x1, x2, xl is a linearly independent set. All right. Hello.
Okay, sir.
Now an immediate corollary comes here. If this L matches with the dimension of V, then what is the character of T? Can you just tell me?
It will be diagonalizing.
It will be diagonalizing. That is what I want. Yeah. Because the matrix of T with respect to this basis would be a diagonal matrix whose diagonal entries are lambda 1, lambda 2, lambda n. Exactly. Right?
Yes, sir.
If L is equal to n, then T is diagonalizing. But we have to look into the more complicated situations. Here, just we have put a strong condition that each of lambda I is distinct. No lambda I is being repeated. No lambda I is being. Hello. Hello.
Yes, sir. Yes, sir.
Here we have put a condition that no lambda I is being repeated, but this is not the case. There may be the operators where lambda is being repeated, but still they are diagonalizable. So for that we have to work more. So look at one more corollary, which is as let T belonging to LV and say lambda 1, lambda 2, lambda k are distinct eigenvalues. Values if for each I we get the vectors xi1, xi2, xini. For each I, the vectors are linearly independent. Now see, these are the vectors corresponding to the eigenvalue lambda, right? Linearly independent. Then the set x1, 1, x1, 2, and so on, x1 and 1, comma, x2, 1, x2 and 2, and so on, xk1, comma, xknk is also linearly independent. Okay. This is easy to see with the above proof, because Sj we defined as what? Product I1 to k, I is not equal to j, lambda j minus lambda I, inverse of that, here t minus lambda I into I. This is what we defined in the above proposition. Okay. Now I claim that this set is linearly independent. So I assume that suppose this sum is 0, linear sum, which is given by say R1 to N K summation I1 to K alpha IR XIR. I just take the linear combination of these vectors, which is 0. And if I can be able to prove that these alpha IRs are zeros, then I'm done. Okay. Hello. Hello.
Yes, sir.
Sir, can you please explain this again?
Yeah. What is the statement? Here we are taking any operator and we are taking k different eigenvalues of this. With respect to each eigenvalue, I am getting a set of linearly independent vectors. All right. Then what I want to prove? I want to prove if I just take the unions of this these sets, that is linearly independent. This is what I wanted.
So here we are not considering the product, right? Because you like here you have written x11 into x12 into x1n.
No. This is a set of the vectors.
Okay.
No, this is not a product. You cannot take the product of the vectors. All right?
Yes, sir.
You cannot take the product of the vectors. So linearly independent. So for the linearly independence, what I wanted, I just take this linear combination 0. If I can prove that each of lambda ER, which is belonging to my field, is 0, then the set is linearly independent. This is what I wanted. Okay? Hello?
Okay.
Yes, sir.
Yes, sir.
You just choose this Sj and apply this Sj on this. Since this is a 0 vector, so when you apply Sj on that, this would lead to 0. What is left here because of this? Just tell me. This is R starting from 1 to nj. Yeah, alpha j R X. Yes. J R. Is that okay or not? It is easy to see. You can just make your quick calculations from here also. Because when you are taking these xi's different, this gives you xl or xj, because j is equal to L in this case. All right. So here again I get this, but this set is x1r, x2r, and xjr. This is a linearly independent set. And that means what? Alpha j r are 0 for r1, 2, and j. And this you can apply for all j's and j. And that means this all alpha ERs are zeros. Zeros. And that is the requirement, what I said, that this set is linearly independent. This means x11, x12, x1n1, comma x2, x21, comma x22, and so on, x2 and 2, and then xk1, xk and k.
Hello. Hello.
Hello.
So, but in the last expression, the first index is fixed in xjr. So how are you taking this x1r, x2r, xjr is linearly independent?
This one?
See,
this is given to me.
No.
For each child.
In the expression, you are varying r. But
R is varying from 1 to nj.
Yes, nj. And so here my j is fixed.
J is fixed. So for I is equal to j, they are linearly independent. For I is equal to j, these vectors are linearly independent up to nj. J1, J2, J and J. They are linearly independent. And therefore in this combination, these coefficients are 0. Okay.
So in the next line, you should write J.
Right. J, yes. You should write xj xj1,
xj2,
xj and j.
x1.
xj alpha jr.
In the next line.
Yeah. Yeah, sorry.
Here, yes,
This is this. Yeah, we must write j. I just have written
Yes.
something wrong. This one.
Yes.
Let me make that correction. Yeah. Here it would be xj1, comma xj2 and xj and j. This implies this. Okay.
Yes.
But this is true
Yes,
for
yes.
all j's. If you just vary j,
Yeah.
j would vary, and that would lead to all alpha irs are 0.
Now it is fine.
Okay. And that means
Okay.
this is a linearly independent set. Now I come to definition. See here. Lambda I was the eigenvector. Sorry, eigenvalue of t, right? And you are getting now, as per this proposition, you are getting several vectors which are linearly independent with respect to lambda. Exactly. Hello. Hello.
Yes, sir. Yes, sir.
Yeah. Lambda I, you are, as per this proposition, you are getting several vectors which are linearly independent with respect to this lambda. Now, if I just collect all the linearly independent vectors with respect to this lambda I, and I just count them, the number of all linearly independent vectors with respect to this lambda I, that is known as the geometric multiplicity T of lambda I. Is that, could you get my point? This is basically the dimension of kernel of T minus lambda I. Hello?
Yes, sir.
Yes, sir.
Dimension of kernel of, because they all would be belonging to this kernel. All right. And there is another which is known as algebraic multiplicity. So if lambda is occurring in its CTX, I just take the characteristic polynomial. Of T. Lambda is occurring in the CTX, the factors, that means the number of is equal to, this is equal to the number of x minus lambda is occurring here, occurring. In CTX, that is characteristic polynomial of T. That is known as algebraic multiplicity. So let us make the difference between these two. One is algebraic multiplicity and other is the geometric multiplicity. Hello. Hello.
Yes, sir.
One is the algebraic multiplicity and other is the geometric multiplicity. Geometric multiplicity is the dimension of kernel of T minus lambda I, and algebraic multiplicity is the number of factors of x minus lambda I occurring in CTX, right? That is known as algebraic multiplicity. So they may be different. You can see some examples. We shall be discussing those examples in the tutorial class, right? So these two may be different. They may be same as well. But another result which we are now going to look at, the geometric multiplicity of an eigenvalue of T is always less than or equal to its algebraic multiplicity. This is another result we are going to look at. Okay. CTX, let me just explain here what is CTX. CTX is basically the determinant xi minus t. Okay.
So, sir, 5 minutes more are there.
Okay, no problem. Let me just explain this. So, proof. Let T is in LV. The geometric multiplicity. Suppose the geometric multiplicity. Suppose the geometric multiplicity of lambda is R. That is, we have R linearly independent vectors which are eigenvectors of T. Are eigenvectors of T with respect to lambda, right? They are moreover linearly independent, right? If R is n, then what would happen? Where n is the dimension of V. Hello?
Yes, sir. Yes, sir.
If R is n, which is dimension of V, then what would happen?
At basis x1 to xr, and then
T would be diagonalizable.
The T will be equivalent to lambda times I.
The matrix of T with respect to this basis, if I just take P basis as these eigenvectors, then this is exactly lambda times IN. Is that okay? And then what is CTX?
X minus lambda.
X minus lambda raised to the power n. Then what is the geometric multiplicity of lambda?
N.
Algebraic multiplicity of lambda, that is n. So here in this case, the geometric multiplicity and algebraic multiplicity, they are coinciding. So case 2, I just assume that R is less than n. If R is less than n, then I can extend then x1, x2, xr can be extended to a basis of V. Is that okay? And if I just take this basis x1, x2, xr with yr plus 1 and so on by n. And what can you say about the matrix of T with respect to this basis? Yeah. This is lambda times IR, but certainly 0 here. This is C sum matrix. This is B sum matrix. This is a block matrix. These blocks are suitable matrices. This is R by R. This is n minus R rows रहेंगी इसमें. There would be n minus R rows. And how many columns? R columns. So this is n minus R by R. This is suitable. This is n minus R by n minus R. And this is also accordingly, you can check that. Here would be how many rows? R rows, column n minus R. Then what is CTX? CTX is x minus lambda raised to the power R into determinant x by n minus R minus B. Check that. Okay. No lambda is being repeated here because the geometric multiplicity of lambda is taken as R. Right. Here, what is the algebraic multiplicity of this?
Greater than or equal to.
Lambda is? Hello?
So it is greater than or equal to R.
Greater than equal to R. R factors are coming. Some
Yeah.
factors here may also be coming.
Yes.
Lambda algebraic multiplicity is greater than or equal to R. And that is what we want to prove, that geometric multiplicity is always less than or equal to algebraic multiplicity. Don't take this as geometric mean. This is, however, true for that. Geometric multiplicity of lambda I take, algebraic multiplicity of lambda I take. Okay. So let me finish here, and we shall be now reaching to the diagonalization, which we shall be discussing in the next lecture. And in the evening, we shall be decomposing V for various operators, right, in the numerical examples. Okay. Any question up to here? Hello. Hello, Rajesh ji.
Yes. Participants, any question? No, then we thanks Professor Mandeep and we meet him tomorrow and also in tutorial.
Yeah, tutorial. That is 2:30 to 3:30, है ना?
Yes, 2:30.
Okay. So done.